We're now going to look at the acids and bases, and we're going to first look at autoionization of water. So it turns out that pure water, which is liquid, will a small fraction of the water molecules in a sample of water will autoionize or break up into ions. You do hydrogen ions and hydroxide ions. And for every water molecule that breaks apart, you get exactly one hydrogen ion and one hydroxide ion. It turns out that in pure water, it's a very, very small amount, and they are going to be equal. So when you see this type of notation here with brackets, that is going to be considered the molar concentration, or moles per liter. So when water autoionizes in pure water, you're going to get a concentration of 1 times 10 to the negative 7 moles per liter of hydrogen ions in water, and that can simply be written as 10 to the negative 7. The same would be true for hydroxide. Would have the same concentration because it's a 1-to-1 ratio. Understanding that then, that when water autoionizes, it's going to be a 1-to-1 ratio, then this will help us understand what makes an acid and a base. So what is an acid? An acid is any substance that when dissolved in water gives up or donates protons or hydrogen ions. So what does that do? That's going to increase the concentration of protons. And a base would do the opposite. A base is going to be any substance that removes them, hydrogen ions, from solution. Not to remove them is not like literally knocking them out of the solution. It's just going to pick them up and hold on to them so they're not freely dissolved as hydrogen ions, so they get picked up. Acids and bases are both electrolytes. They do ionize and dissociate in water. Acids, as I mentioned before, are going to be proton donors. They give them up. And an example is going to be hydrochloric acid. It's a strong acid and it gives up hydrogen ions. It also gives up chloride ions, but they're just going to be in there spectating. They're not going to have anything to do with whether or not you have an acid or a base. So some important acids in human physiology include hydrochloric acid, which you can find in your stomach. There are cells that secrete that. There's acetic acid. This one's a weak acid, and we'll talk about weak acids in a bit. And there's carbonic acid, which is, you can find that in your blood. This acid is involved in helping maintain pH balance or acid balance in your blood. And so a base then is something that I said earlier removes protons. We can also say that they accept protons, which means they're going to pick up hydrogen ions from solution. And an example there is a common laboratory base called sodium hydroxide. When you dissolve it in water, it picks up it dissociates and forms sodium ions and hydroxide ions. And hydroxide ions really love to pick up protons. And if they pick up protons, if hydroxide combines with a proton, then your result is going to be water, H2O. HOH is H2O. Some important bases in the human body include, or in your physiological, include the bicarbonate ion and the ammonia molecule. The ammonia molecule can actually act as a weak base, and that it can attract these protons to it. The chemistry for that is beyond the scope here, but just be aware that the ammonia ion itself can pick up hydrogen ions and basically keep them from being free in the solution. So that can influence the acid base of the water or the solution itself. So here's the pH scale. It's used to measure pH. It's used to measure how acid a solution is. So I'm going to draw another scale here on the bottom. And this scale is going to be the concentration of protons. And it's going to be in moles per liter. So when you read this pH scale, it's actually referring to the concentration of hydrogen ions. And the more hydrogen ions you have in solution, the higher the concentration, the more acid it's going to be. Likewise, the lower in the solution, the lower the high, it's going to be more basic. Okay, so one thing to be aware of is that as we go along the scale in this direction, the hydrogen ion concentration is going to be increasing. And that seems a little bit weird, because if you look at the pH scale up here, as we go to the left, the scale is actually getting lower, right? So to help us understand that, we need to see, well, what's actually going on. So I'm going to draw the hydrogen ion concentration scale here. A pH of 7 actually corresponds to 10 to the negative 7 moles per liter of hydrogen ions. And so 6 would be 10 to the negative 6, 5 would be 10 to the negative 5. So those numbers are actually represent the exponent without the negative sign. So a pH of 4 would be 10 to the negative 4. And a pH of 1 would be 10 to the negative 1. Okay, so if we think about it, 10 to the negative 1 is actually really the same as 0.1. 10 to the negative 4 would be 0.0001, and that's a lot smaller. So it's 0.0001 moles per liter when your pH is 4, but only 0.1, or should I say 0.1 moles per liter at a pH of 1. And this is bigger by many orders of 10 bigger. And so if we go back the other way, we're going to get smaller and smaller hydrogen ion concentrations. For example, pH of 10 would be 10 to the negative 10 moles per liter of hydrogen ions, and a pH of 13 would be 10 to the negative 13. So, and that would be an extremely small number. That would be like 0.000, that's 3. We got to keep going. 6. 9, so that's tenths, hundreds, thousands, so we got to keep going. 9, 10, 11, 12, 13. So it'd be that small amount of hydrogen ions, moles of hydrogen ions per liter. So this brings up what the definition of the pH scale is. pH is the negative log of the hydrogen ion concentration. And logarithms, or the most common logarithm, is that with a base 10. And the answer to a logarithm is the exponent. So the exponent represents the actual number. So if I were to say log base 10 of a value 10 to the 3, my answer would equal to 3. If I were to say log, and I'm not going to write the 10 anymore because if it's not written, it's understood. If I said log of 10 to the negative 3, my answer would be negative 3. So the answer is the exponent. And if you know you're on a log scale, then negative 3 would be equal to, on a log scale, negative 3 would be equal to 10 to the negative 3, which is a small number. It's 0.0001. So keeping that in mind, it now makes sense that if we have a pH of 7, the pH of 7 corresponds to a hydrogen ion concentration of 10 to the negative 7. And if we put 10 to the negative 7 in there, then we're going to get an answer of negative 7, but we have to take the negative of that. So the negative of that changes the sign, so we get 7. So that explains the definition, and it's a good idea to keep in mind this equation here. And it really explains why when you go smaller on the pH scale, you're really getting a higher hydrogen ion concentration. So we're talking about the pH scale here, and kind of define that for you here. Here is the actual way it's written in words. pH is a negative logarithm of hydrogen ions in moles per liter, and it can range from 0 to 14 like we saw in the previous slide. And so something to keep in mind, this is a log base 10 scale. So every time you move a unit, pH unit, you're actually changing by a factor of 10, or a tenfold change. So it's a tenfold change. So we look at the example here. It says a pH of 5 solution is 10 times more acidic, which means it has 10 times the concentration of hydrogen ions than one that's a pH of 6. Let's go illustrate that back on our previous slide here. So if I were to start with a pH of 7 and then I pour an acid into solution, which is going to increase the amount of hydrogen ions in solution, and it increases it to a pH of 5. The change in the hydrogen ion concentration, the factor that it changes by is actually 100, because each unit step is a factor of 10. So that's 10 times 10. So 10 times 10 is 100. If I were to add an acid enough to change it to a pH of 2, by what factor did the hydrogen ion concentration actually change? That's 10 times 10 times 10 times 10 times 10. So that's a factor or 5 orders of 10 that it changed. So that would be 10 to the 5 or 100,000 change. Now if I add a base, the base is going to pick up hydrogen ions from the solution, so it'll remove them, so you start having less and less. So if I go from a pH of 7 to 11, the factor that I change by is, well, how many steps is that going to the right? It's going to be 1, 2, 3, 4. So that would be 10 to the 4 times smaller, which would be 1 over 10 to the 4, which is 1 over 10,000, so it'd be 10,000 times smaller, or a factor change of 1 over 1,000 in terms of what the pH, what the hydrogen ion concentration changed by. When it comes to the scale, the pH scale, anytime you're at 7, you're neutral, and you're going to be acidic if your hydrogen ion concentration has a pH of less than 7, so that's going to range from 0 to 6.99. You're going to be neutral, as I said, when you have a pH of 7, and I brought up this, there's an error here. It should be moles per liter as far as what the actual concentration is at a pH of 7. And you're going to be alkaline, which is another word for basic, if your pH is between 7.01 and 14. In other words, if it's higher than 7. Okay, so here's our pH scale, and it we can ignore this. This has to do with another scale called a pOH. But here shows your pH scale, which we've been talking about. So you can see right here, if we have a pH of 7, that corresponds to our, coming back here at the top, our hydrogen ion concentration of 10 to the negative 7. If we were to apply that formula for pH, negative log of hydrogen ion concentration, that would give us an answer of 7. And we can see over here we have less acidic or more basic. And then when we go lower on this scale written, it would be more acidic. And then here you just have some common items that we see every day that shows their pHs, or what their pHs would be. So when it comes to acids and bases, both can be quite reactive, and in extreme cases, when you have a strong acid or a strong base, they can be caustic, which means they can cause damage to tissues, chemical burns, and so on. So if we do have an acid, though, we can actually neutralize it with a base. And it turns out that it is a double displacement reaction. So it's a displacement reaction where what we start with, these two items are going to switch places. So if we start with a strong base, sodium hydroxide, and we put it in solution, it's going to create sodium ions and hydroxide ions. And if we put hydrochloric acid in there, it's going to create hydrogen ions and chloride ions. And what's going to happen here is we have a strong base here. The hydroxide is going to love to pick up these hydrogen ions, so those two are going to combine and form water. And what are we going to get? We're going to get a salt, in this case table salt. So that brings up something important to remember, that during a neutralization reaction between acids and bases, your result is going to be a salt during the neutralization and water. That's what your products are going to be during neutralization. So with acids and bases, another concept comes up called buffers. And buffers are important in our system because they help prevent pH from changing wildly. If the pH changes too much, that can be a disaster, because your metabolism will not work correctly, because your enzymes will change shape, and your enzymes are what helps regulate your metabolism. So before we start talking about buffers, it would be important here to talk about what a reversible reaction is. So reversible reactions are reactions that can go in either direction. So a lot of times we're going to draw a chemical equation where the reaction only goes to the right. But sometimes the products are going to go through a reaction in the opposite direction and reform what they started out to be. Okay, so during these types of reversible reactions, there's going to be some sort of an equilibrium. So these reversible reactions reach an equilibrium between the reactants and the products. And I'm going to illustrate that down here, but just a couple of points need to be made. The equilibrium point depends on the specific reaction, so it depends on the substances that are going through reaction. Each one is going to have a different equilibrium point. In other words, how much relative to the reactants on the left, how much products are you going to get. There's going to be a certain amount. So you might have, for every 20 molecules on the left, or particles on the left that are reacting, you might only get one on the right. And that ratio will stay pretty consistent. So that equilibrium point will depend on what you have. And these reversible reactions are going to follow what's called the law of mass action. And that means that in a reaction, if you add a product, the reaction will shift to the left. So the equilibrium point is going to try to maintain that same ratio of reactants and products. So if you add product on the right side of the equation, you're going to have it shift back to the left so that it balances out. And I'm going to illustrate it down here again. And we can do the same for the reaction. If we add reactant, that is, if we add stuff on the left, then the reaction will shift to the right. So here's an example of an equilibrium or a reaction with carbonic acid. If we put carbonic acid in water, it's going to dissociate into protons and bicarbonate ions. So it's going to break apart. Now for this reaction, let's say that, for example, that every 20 of these molecules, only one is going to dissociate. And as soon as it dissociates, it comes right back to carbonic acid form. Okay? And as soon as that happens, well, another one dissociates. So more or less, there's always going to be about a 20 carbonic acid. Every 20 carbonic acids, only one's going to dissociate. So that ratio is going to be about the same. So it's an equilibrium at that point. Regardless of how much carbonic acid we put in there, about 1 in 20 are going to dissociate. So I ask now the question, we try to apply this law of mass action that I talked about above. And it says that if we add product, the reaction will shift to the right. Or if we add product, the reaction will shift to the left. So here's a question based on that. It says, what happens if we add more bicarbonate? Well, bicarbonate is a product. It's on the right side. If I add more than that, it says, going back up here, it says, if we add more product, it's going to shift to the left. In other words, if I add more of this, our ratio is going to be thrown off. We're not going to have 20 to 1 anymore. So what's going to happen if I add more of this, we're going to shift back to the left. Okay? And it says now, if we add more reactant, the reaction shifts to the right. So what if I were to add more carbonic acid? Well, that means we're going to shift to the right until we get back to that ratio of for every 20 carbonic acid molecules, we get 1. So here's another question now to consider. Both of the rules that I brought up here for law of mass action say if we add. Well, what if we take away? If we take away, then the same thing, we would see the same thing happen, except in opposite. So if you take away, then the opposite would happen. So if we were to reduce product, then the reaction is going to shift in the opposite direction, to the right instead. So the opposites are going to hold. So here we say now, what happens if we remove hydrogen ions? In my question number 2 here. So if I were to remove hydrogen ions from there, we're no longer going to be in that ratio where we have 20 carbonic acids to 1 proton. So what's going to happen is it's going to shift in the same direction when we remove. Okay. Now that's important to understand where buffers are concerned, because buffers, and in fact, carbonic acid and bicarbonate serve as buffers in your blood. So when we work with those, then with these types of buffering systems, they tend to be things like weak acids and weak bases. So our carbonic acid here is a weak acid, and a bicarbonate ion is a weak base. So let's say we have this in a solution. We have carbonic acid and bicarbonate ions. They're in equilibrium. And I were to add a strong acid like hydrochloric acid. When that dissolves in water, it's going to produce an increase. It's going to produce hydrogen ions. They're going to dissociate, like we showed you earlier, and that's going to increase the amount of hydrogen ions. If we apply the law of mass action here, and we're adding more hydrogen ions, we're adding more product, that's going to shift the reaction to the left. If it does, that's going to encourage the extra hydrogen ions to bond with our weak base, the bicarbonate, and shift to the left. So we're going to end up forming more of these until we hit that equilibrium, until we get to where we have 20 carbonic acids to 1 bicarbonate, roughly. Right? That would be the case when you add an acid. Well, what if we add a base? Let's say we have the same solution, and instead we add a base like sodium hydroxide. When sodium hydroxide dissolves in that solution with the carbonic acid bicarbonate buffer, we're going to end up adding hydroxide, because it's going to dissociate. The sodium hydroxide will dissociate into hydroxide ions, and those hydroxide ions love protons. So those protons are going to combine with hydroxide, and that's going to decrease the hydrogen ions. So when we decrease the hydrogen ions, we're taking them away. That's going to shift the reaction to the right. And when we shift it to the right, that's going to add more protons to solution and overall help balance out what had been taken away, so the pH would stay roughly the same. So that's kind of what buffers are. Buffers basically are going to prevent, like I said, massive swings, and we can use the massive swings in pH, and we can use the law of mass action to explain why. So here's the actual slide that defines buffers. Acidity involves the only free hydrogen ions, not any hydrogen ions that are going to be bound to anions. So acidity depends on how much of this you have. That's what the pH scale is, right? So what are buffers going to do? Buffers are going to resist abrupt, quick changes and large swings in pH. They can release hydrogen ions when the pH rises. When the pH rises, you have less hydrogen ions because you're going to a higher number of pH, as explained earlier. And buffers can bind to hydrogen ions when the pH falls. When the pH falls, that means you're having more hydrogen ions. So if you have more hydrogen ions, they're going to bind to the buffering agent. Okay? So this statement here is a little bit confusing. So what we want to do is sort of ignore it and just go with what was explained earlier. And I did explain the carbonic acid bicarbonate as a buffering system. And here it's just kind of summarized the way it is in the book. You have your bicarbonate ion. It's a hydrogen ion donor, which makes it a weak acid. And then our bicarbonate ion, which is right here, is a weak base. It's a proton acceptor. And then there's a proton there. And then it's kind of illustrated here on the double-sided arrow. If we're going to go to the right, that's because that's going to be a response to the rise in pH. When you rise in pH, that means you have less hydrogen ions. Okay? When you have less hydrogen ions, more of the carbonic acid is going to dissociate to the right and help us maintain adequate number of protons. So we're going to add more when the pH rises. If we're going to go to the left, that's going to happen when our pH drops. There's a drop in pH. That might happen if we add more acid to the solution. We add more acid to the solution, basically we are increasing the amount of protons. So when we add more here, according to the law of mass action, that's going to shift the reaction to the left. Those protons are going to bind with this weak base and form carbonic acid, so we would no longer have, or we would reduce the amount of free protons there, and overall that is going to shift until you hit that balance again, that equilibrium, and that helps to maintain your pH and keep the pH from changing too wildly.